for both rows.
Right.
Just wanted to kind of recap what you said. An inverse of a matrix is just a particular kind of transpose that only exists for square matrices.
No.
Oh,
Only square matrices have inverses.
okay.
Sometimes when you're lucky, the inverse is equal to the transpose. And that's actually the one section we skipped. So an orthogonal matrix in 5.3 that we skipped is a matrix that has that property.
Okay.
Okay, then I can imagine having an idea of a left inverse and a right inverse. So normally, when we just say the inverse is on the square matrices, and whether I do A times A inverse or A inverse times A, they don't give each other. But sometimes this works as a right inverse, sometimes it works as a left inverse. So this is a non-square matrix. I could have a right inverse or not. I could have a left inverse or not. And there's no way they're going to be the same. So more than you know, is that cool?
Yeah, yeah.
Which one?
I'm a little confused about the column space matrix.
Okay.
When you use that for the QR factorization, so you wanted to use the original column space?
Yeah, and the reason why, what I wanted to do was, so what the QR factorization does
Right.
is it breaks a given matrix down into a product of two matrices. And this is an important breakdown in later algebra classes. And the properties of these matrices are the columns of Q form an orthonormal basis for the space spanned by the columns of C. Or C and Q have the same column space. Columns of Q form an orthonormal basis for that. And then R is the matrix that makes the factorization work out. And R ends up being upper triangular.
We didn't go back and back.
We just calculated Q now.
Okay.
That's the way we're going to do it, is to find the orthogonal matrix Q, and then orthonormal matrix Q, and then pretty much just divide out by n bar.
So we don't divide it.
Right.
Bulk by Q transfer.
Yeah.
That's the idea. Was there one more question?
Professor, why you have the equal square root of 25? 35 because I have the results of 7 over that's right. 39 square root.
Oh, 7 over what?
7 over square root 35.
Oh, okay. Sounds good. So I was just guessing. Oh, no, that's right. Because that's actually what I had for the, you're right. That was what I had for the, that was the magnitude, wasn't it? W2. Yeah, I was just guessing. I misremembered.
The magnitude of W2
Yeah, so it was 5. So anyway, this does end up being the magnitude of W2 curve.
Yeah, but when using the magnitude of W2 it was 35.
Right, okay, so it's some number.
Okay.
So I'm going to leave it to the arithmetic, and if you do Q transpose times C, you can see exactly what that number is. At one point, I probably should figure out. All right, we'll move on. So, probably the technique that you'll be using the most often in this class. And overall, it's a good thing, but sometimes it's not. Is this technique is so important that it's built into any software you'd be using to analyze it. The idea is you've got a system of equations where if you knew the solution to that system, it would tell you about the object that you're studying. And unfortunately, there's no numbers m and b that make all those equations true. So it's your job to figure out the best possible m and b. So what do you think about m equals 0, b equals 1? Makes the first one true, makes the second one true, and the third one, not bad. What about m equals 10, b equals 20? That'd be terrible, right? So some m's and b's are better than others. And linear algebra makes it precise what the best solution would be. So linear algebra gives you a way to compare two solutions. So is a matrix. You can write it like this. We went through a fairly long process. And the end of it just showed us the simple way to solve this. What do we do to both sides? So if I've got an AX equals B that doesn't have a solution, multiply both sides by what? And remember, the transpose of a matrix is I'm reading down the column and writing it as a row. So the first column, -1, 1, 2, I write that as the row. And one thing I've been doing for a long time is doing the same thing to both sides of the equation. So this is going to give me 2 by 2 times the 2 by 1 times the 2 by 1. 1, 2, I got a 6 there, correct me if I'm wrong. 2. So the nice thing, these are going to be symmetric, so that has to be a 2, and then finally 3. And then 6. Excellent. And that looks like a more reasonable system of equations. 6m plus 2b is 6. 2m plus 3b is 5. You may or may not be able to do that in your head. You could work it out by putting it into an augmented matrix and going reduced to echelon form. A second way to do it, more algebra way to do it, is to multiply both sides by A inverse. So if I call this AX equals B, I can multiply both sides here by A inverse. A inverse and A cancel each other out, and I get out of line the M and T. So the inverse of this is whatever it is. Okay, the crisscross is 1 over what? So I say determinant now, what those were. 6 times 3, 18, minus 4 is 14. Switch these two, make those negative. So if I want the solution to this, one over 14, that's 3 negative 2. And 6, 5?
Yes.
This is 1 over 14, 18 minus 10 is 8, negative 12 plus 30 is 12.
18. Yeah.
18?
Yeah.
Negative 12 and 30 is 18. So this, you guys like fractions, is 8 over 14, which is 4 over 7. So the best solution. Let's see how that does. So what I want is negative m plus b is 1. M plus b, what's it?
No, that's just solving.
So let's see how we did. You know, the picture here is important. So if I do negative m plus b, I get 5 over 7. If I do m plus b, that is 13 over 7. And 2m plus b is what? 17%. So the right way to look at this, I can challenge you, you cannot do better.
I'm surprised that it's so far.
So the idea is, so here's the vector 1, 1, 3. And here is the vector 5 sevenths, 13 sevenths, and 17 sevenths. And the way we're measuring how good a solution is the distance between those two. So there's no other numbers. Oh, hold on. So there's no other numbers that you could plug into this to make it back to make these numbers closer to 113 than 4 over 7, 9 over 7. This is the best you can do to get these components close to those.
So,
And actually, while we're there, it's the real picture is under new part C.